Swayam Prabha. Digital India. Educated India.
So in continuation of the finding the circuit, next most important algorithm is shortest path algorithm. So a large number of optimization problem are mathematically equivalent to finding the shortest path in a graph. Consequently, the shortest path algorithm have been worked over more thoroughly than any other algorithm in graph theory. So, more than 100 papers have been published and dozens of algorithms have been proposed. Some of these algorithms are better than others, some are more suited for a particular structure than others, and some are only minor variation of earlier algorithm. For good comparative study of a very shortest path algorithm through the year 1968 and a survey paper as a Dreyfus is highly recommended. Please refer it. There are different types of shortest path problem most frequently encountered among these are the following, 5 of which we shall solve the first 3. That is, the flow chart says that read x comma y when p takes 0 and k equal to 1 and p1 equal to 1 and h is equal to 0, then I equal to p1 plus 1 is I is greater than n. If you say yes, then you have to move is these are a directed edge, and if pk is p1 or directed, yes mean print it, otherwise no mean start with k equal to 1. Further, if k equal to 1, if you say yes, then p1 equal to p1 plus 1 you go, and pk equal to p1 you go, and if pk is n, then you go to loop that is less than or greater than, or the two things. If vertices are greater than, then stop it, if less than, and go to the yes. If k equal to 1, no mean clear the list of the forbidden vertices from pk and make pk forbidden from pk minus 1. If pk equal to 0 and k equal to k minus 1, go to the loop, start from the p1 equal to p1 plus 1, and if I is greater than n is no, is there a directed edge from pk to I? If you say yes, is I in p is this directed edge pk comma 1 no mean you have to further go I equal to I plus 1, and is I equal to I in p and then yes mean once again you go to I equal to I plus 1. Is the vertex I forbidden from the vertex pk? If yes mean go to I equal to I plus 1, no mean k equal to k plus 1, and pk you have to count and proceed p1 plus 1, p2 plus 1 and so on, and go ahead, and then if final reaches, stop the iteration. So this way we can find the directed circuits. So the 5 points are shortest path between the 2 specified vertices, shortest path between all pairs of vertices, shortest path from a specified vertex to all others, shortest path between specified vertex that passes through the specified vertices, and it moves the second, third and so on is the shortest path. In a worst case situation, the type 1 becomes identically equal to 0, because in the process of finding the shortest path from a specific vertex to another specific vertex, we may have to determine the shortest path to all other vertices. So let us deal with the type 1 first. Next, algorithm, shortest path from a specified vertex to another specified vertex. So the problem of finding the shortest path from a specific vertex S to another specific vertex T can be stated as follows. So the simple weighted diagram G of n vertices is described by n cross n matrices where D equal to Dij. If Dij is a length or a distance or weight of a directed edge from vertex I to vertex j, then if it is positive, If dij equal to 0, if dij is infinity, there is no edge from I to j. So, this is the condition you have to use for the shortest path from one vertex to the another vertex. In general, if dij not equal to dji and the triangle inequality need not be satisfied, that is dij equal to djk plus djk may be less than dik. Therefore, the problem would be trivial because the directed edge x comma y would be the shortest path from vertex x to vertex y. So, the distance of a directed path p is defined as a sum of the lengths of the edges in p. So, the problem is to find the shortest possible path and its length from a starting vertex s to the terminal vertex t. Among several algorithms have been proposed for the shortest path between the specified vertex pair. Perhaps the most efficient one is an algorithm due to Dijkstra. So, this is a very good algorithm for finding the shortest path from one vertex to the another vertex. Now, we are going to describe the algorithm. Dijkstra's algorithm label the vertices of the given diagram. At each stage in the algorithm, some vertices have permanent label and other temporary labels. So, the algorithm begins by assigning a permanent label 0 to the starting vertex s and temporary label infinity to the remaining n minus 1 vertices. From then on, in each iteration, another vertex gets a permanent label according to the following rule. Number 1, every vertex j that is not yet permanently labeled get a new temporary label whose value is given by minimum of old label of j, comma, old label of I plus dij, where I is a latest vertex permanently labeled. In the previous iteration, dij is a direct distance between the vertices I and j. If I and j are not joined by an edge, then dij equal to infinity. So, this is the things you have to remember. It is very important. You take a old label j and old label j plus the distance you take it, which one is the minimum, that you have to take it. Next one is the smallest value among all the temporary label is found, and this becomes a permanent label of the corresponding vertex. In the case of tie, select any one of the candidate for the permanent labeling and repeat the step 1 and 2 alternatively until the destination t gets a permanent label. So, the first vertex is permanently labeled, is at a distance of 0 from S. Second vertex to get permanent label is the vertex close to S. From the remaining n minus 2 vertices, the next one to be permanently labeled is the second closest vertex to S, and so on. So, the permanent label of each vertex is the shortest distance of the vertex from S. So, this statement can be proved by induction. As an illustration by Dijkstra's procedure, let us find the distance from vertex B to G in a graph shown in the figure. So, we shall use the vector of length 7 to show the temporary and permanent label of the vertices. As we go through the solution, the permanent label will be shown enclosed in the square, and the most recently assigned the permanent label is a vector indicated by the tick. So, the labeling process as follows. So, this is the procedure. Now, you take starting a vertex B and can label 0, and you take A, B, C, D, totally A, B, C, D, F, G, totally these vertices, and now let us start A. Initially A is a no self loop, therefore M in infinity you have to put it as per the definition, and from B, vertex B is labeled 0, therefore 0, and B to C, initially you have to what the smallest label becomes permanent successor of C get labeled, and initially first connected with B to C, B to D, B to E, B to F, like that you have to do. All are no successor of this, therefore B is starting, all successor of B get label, and now you have to start with B to A. B to A there is a connection 7, and initially already chosen B, therefore everything that column put 0, and B to C is 1, therefore 1 here, and B to D there is no connection, therefore infinity, 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 rest of them no connection. Then you have to take next B, next A you have to take it, and which one is the smallest you have to take it from the row 2, 0, then you have to connect with B to the previous one, and then rest of them will be what? B to A is 7 and B to C is 1, and then rest of the infinity. Compare with this third row, which one is next to minimum? 1, and then rule apply it, right, and minimum of the rule is minimum of old label j comma old label of I plus dij. So old label of I is 0, 0 plus 1 is 1, and compare with 0 plus 7, 7, and among the minimum is 1, therefore 1 you put it box. Next you have to take C, right, the connect with C to A, right, C to A, yeah, C to A is there, and then we have a what minimum of the old one 7 and minimum of old one plus dij. So 1 plus 3 is 4, therefore it becomes 4. So minimum is 4, and then 0, 1 as usual, and then connect with C to E is 4 plus 1 is 5, 4 plus 1 is 5, and then next connected with C to F. C to F is already 1 plus 3 and minimum is 4, and then rest of them infinity. Now you take the fourth row, which one is a minimum? 1 is a minimum, and then you have to what connect with all this is 4, 0, 1, infinity, 5, 4, infinity. Now among these next minimum is what 4, here 4 tie up because of the successor we have to follow, therefore you have to go to the F, C to F. So we have to put a box, and this old one you have to take it. Now you compare with the formula minimum of old label of j, minimum of old label of j comma old label of I plus dij. So this idea you have to do here, and then what happened? 4 along with what compare with that one is 4, 0, 1, and here connected with F to D. So F to D, right, then we have minimum of old, that is old one is 4 connected with F2 D, right. So we have 7 plus 2 plus 4, 9 plus 4 is 9 plus 4, that is 9 plus 4 plus 1, that is 1 is also enclosed, therefore 14 will come plus dij, and then so we have 0, 4, 0, 1, 14, 5 and 14, and next E to sorry F to G, F to G is 7, therefore so we have what 1 plus 3 plus 7, so it becomes 11. Now you take the 1, 2, 3, 4, 5, sixth row. Sixth row, which one is the next least? The 4 already taken. Now this 4 you have to take it and connect with A. So this A you have to connect and comparative with the other connection with the A to other A to B, because already boxed you do not bother. Go to D, A to D, we have a 8. So new one is here is not altered, therefore 14 keep as it is, and then 5, 4, 11 as it is will come. Now compare them. So 1 to 3, 3 to 8. So 9 plus 3, then 12 will come, and then 5, 4, 11. So among this one is, which one is the minimum? Already 4 taken, only thing is 5 only minimum, and then once again do the process with the connection with the E. Therefore E to A now already taken, no issue, only E to D. E to D is no connection. So E to D is we have to go only A to E, E to G, G to D only we have to go. Therefore that will be remain as it is. So no steps have to be taken, simply leave it, and then you go to the what E to G. E to G is possible. Now we have already taken 7 plus 2 is 9 plus 2 is 11 is coming. Now compare with old, then it will comes, which one is a minimum. So 1 to 4, 4 to 1 to 8, B to C, C to E, E to F, F to this, so that it will become 7. So 7 is a minimum that is reached, implies this is what a destination permanently labeled. So this way we can do for labeling of the vertices in a digraph. Now we have a flow chart. Read D, N, S, T, label as no connection, infinity, label, then you start with the vertex 0 and 1. If S equal to 1 and M equal to, then there is no connection, then infinity, the vertex of I equal to 1. If you say no, then Z equal to Dij, which is label of I, and if you say further proceed, the Z is of the label Ij, then no. If you say yes, label to label of I equal to Z, is label of I is greater than Z. If you know, then label of I tends to P equal to I. If you say yes, then is I equal to N. If you say vertex of P is tends to 1, then I equal to P. Is J equal to N, then J, no mean J equal to J plus 1, then proceed further. Otherwise is P equal to R, then S mean print, otherwise you have to go to the loop, then stop the algorithm. This is the way we can find the shortest distance from S to T. So this is the things we have to use the algorithm from the graph of this. So this you have to remember, right? Please remember this picture, and then from the arborescence of this graph is B started and go to C, and then A, and then C to E, E to G, G to D, and then C to F. So this is the shortest distance from one vertex to the another. This is the maximum possibilities we can do. So if you say D is a destination, then the B to C, C to E, E to G, G to D only can do that. So A and F are not terminated, then simply leave it, and then rest of them only have to do that. So this is a way we can find the shortest from B to other vertices, B to A and B to F, B to D. Next, shortest path between all pairs of vertices. So, the description of the algorithm is, the algorithm works by inserting one or more vertices into path whenever it is advantageous to do so, starting the n cross n matrices where D equal to Dij of the direct distances. N is n different matrices design and construction sequentially designed. If k equal to 1 and then D1, D2 and so on, Dn you have to do sequentially, and may be thought of the matrix Ij, the entry gives the length of the shortest directed path among the directed path from I to j, and this allow in intermediate vertices matrix dk equal to 0 is constructed from dk minus 1 according to the following rule: Dijk is equal to minimum of Dijk minus 1 comma dik of k minus 1 plus dkj of k minus t, where k equal to 1 to n and Dij of power 0 equal to Dij. That is the iteration 1, and vertex 1 is inserted the path from I to j, and Dij greater than Dij or Dik is greater than or Di1 greater than D1j plus Dij. In iteration 2, the vertex 2 is inserted and so on. So, for example, the shortest direct path from 7 to 3 is 7, 4, 1, 9 in the following replacement occurred from the figure, this figure, right, 7 to 3, 7, 4, 1, 9, 5, 3, the following replacement occur. Iteration 1, D49 is replaced by D410 plus D10, like that you have to iteration 4, iteration 5, iteration 9, you can go there. Therefore, shortest distance is obtained. So, value of this entry will not be altered in subsequent operation, right. So, the optimal policy matrix Z can be constructed as follows. So, Zij equal to j if Dij is not equal to infinity, if it is 0 Dij equal to infinity. So, the kth iteration, if the matrix K is inserted between I and j, the element Zj Ij is replaced by the current value of Zik for all I and y. Updating the Z matrix is done during the iteration K, and at the end the shortest path will be generated. So, V1 equal to Zij, V2 equal to Zv1ij and so on, j equal to Zvij. So, this example shows that if it is 490 been replaced 41 and 19 connection of 0 iteration of the initial stage of iteration 1. Iteration 4 mean it goes to 3 here, and then 7 3, 7 and 7 4 and 4 9. Similarly, 9 3 is replaced as 9 5 and plus 5 3. So, like that you have to replace the iteration 9 based on the vertex set. So, if read n equal to 0 and k equal to 1 and s equal to 1, if k equal to k plus 1 and s equal to I plus 1, if you say no, is I equal to n no, then you have to go the above, and if you say yes, then k equal to n, and if you say yes, print, otherwise you have to go to the loop. And is dik is less than infinity, if you say yes, I equal to 1, sorry, j equal to 1, is Dij is less than infinity, then x equal to dik plus dkj. If x is less than Dij is s mean dkj maps to s. If you say s equal to j equal to n and then go to s mean, you have to go to know of these ideas and then process, otherwise you have to go j equal to j plus 1, a process going on. So, like that we have a loop, we have a loop here. So, this is the shortest path between the every vertex pair. Next, depth first search on a graph. So, this is the undirected graph and inputted as a neighbor listing, and xb specified vertex from which the search to be begin, and pom and fron are the two disjoint subsets into which the edges G are to be partitioned. Step 1, set V is x I equal to 0 and pom is 0, fron is empty, I equal to I plus 1, number of V equal to I, and look for untraversed edge incident on V. If there is no such edge, go to step 5, otherwise pick the first untraversed edge at V, say u V comma W, and traverse this edge and orient the edge V comma W from V to W. Now you are at the vertex W. Step 4, if W is a vertex which has not been visited, now you are at vertex W. Sorry, if once again, step 4, if W is a vertex which has not been visited before during this search, that is, if NUM of W is undefined, add edge V comma W to the set pom, set V to W and go to step 2. If W is a vertex which has been visited earlier, that is, NUM of W is less than NUM of V, and add edge V comma W to set fron, go to step 3, you are back to at vertex V. Now check to see if there exists some untraversed edge U comma V in set pom oriented toward V. If there is such an edge, move back to the vertex U and set V to U and go to step 2. If there is no such edge, and stop it, and that is the traverse every edge and visited every vertex connected. So the DFS. So DFS mean depth first search. So it is most useful in AI and ML. Therefore, DFS algorithm just described the illustrated in the example. In the given graph, so this is a given graph of 5 vertices and 8 edges. The starting vertex x is specified, the order in which the edges are explored in a given figure, this is a B. Now for traversal G is given, now you start with x, right, x to A. If there is x to A, then you have to do the branch, and then A to B, right, we have a branch x to A to B, and then B to X. So B to X, then this is a circuit formed. Therefore, it is called as fraud, and then B to C, there is a possible, then you have to go, and then there is a branch, right, and C to X. C to X, if you go there, then it becomes a loop, therefore do not do that. And then C to A, that is also a loop will come, a circuit will come, and B to D, there is a branch. So the picture is this 1, this is, if you say 1, so 2, and this is 3, and 3 may be connected to 4 and 4 may be connected to 5. So this is a picture after a DFS method. So this is a technique you have to go with the depth first search on a graph. So this is observed for a performance of a graph theoretic algorithm, and it would be desirable to have an algorithm which guarantee a solution in an execution time and proportional to some constant power of n or e. In other words, the execution time can be expressed as t equal to less than or equal to alpha into n power k and t is less than beta into e power q. So, and the lower the value of k and q, the better. Such an algorithm computation time is bounded by polynomial called a polynomial bounded algorithm. For example, algorithm 1, connectedness and components is a polynomial bounded since k equal to 2, and rest of the algorithm 2 to 8 are also polynomial bounded, but algorithm 5 and 9 are not. Some important polynomial bounded graph theory algorithm along with their bounds and relevant references shown in the table. And note that for the simple graph E less than or equal to n into n minus 1 by 2 less than or equal to n square by 2 is bounds in terms of E and n are convertible into each other, and it should also be kept in mind that different algorithm bounded by the same power of n may take very different amounts of actual computer time because of their different multiplicative constants. So, this is the running time of the relevant references. For the problem connectedness and components, the running time is n square or E, and refer relevant references 11 to 29, 11 to 16 like that mentioned. For all the problems like a spanning tree, we have a E is a bounded time, minimal spanning tree is n square, fundamental circuit set is n power nu, where nu is lies between 2 to 3, cut vertices and blocks is n square or E, bridges is also n square or E, shortest path between the two vertices n square, shortest path between all the vertices n cube, and the transitive closure is n power alpha comma 2 is less than alpha less than 3, strong connectedness and fragments is n square or E, and planarity and topological sorting is E, and maximal matching in the bipartite graph is n power 5 by 2. So, maximal cut is n power beta, where beta lies between 2 to 3, and minimal edge cover is n qm. These are all the corresponding running time of the bounds, and these are all the numbers references, and one may interested refer it. So, this is polynomial bounded algorithm will be helpful, and these are all the problem, and you refer it, and these are all the references. They are chromatic number, smallest dominating set, maximal click, Hamiltonian circuit, directed Hamiltonian circuit, and travelling salesman problem, minimal feedback edge set, minimal feedback vector set, Steiner tree, isomorphism. So, these are all the references, various journals, you refer it, and it will be helpful to attack the problem. And one may refer graph theory and its application by Nursing Dio. You may see these are the listed of references. So, one may refer it, you can get the ideas.